Hello everybody, welcome to the stream. I'll have the live chat open. So if you're online you can say something. I don't think anybody's online yet. 0 people watching, that's fine. Okay, so the questions listed are below. I gotta burn through these because I gotta record 2 of these videos today. So let's get it taken care of. First, page 63, question 39. Oh, someone's at the door. Hold on.
Did I leave these behind?
Yes, you did. Only not those ones. These ones.
Yeah, these can go in the garbage.
What's that?
They're all scratched. They're useless.
Okay.
I'll do it. You don't have to do it.
Thanks.
See ya.
Talk to you later. All right, we're back. Okay, here's my pen. Okay, question 63 says, no, not that page. 63. We have lots of books here. 63. 63, 63. Page 63. Oh, no, wait, it's page 69. Did I have it at 69? Yeah, okay, 69. Question 39. All right, so question 39 says, in this chapter, we saw a person's reaction time is generally not quick enough to allow the person to catch a dollar bill dropped between the fingers. If a typical reaction time in this case is 0.25 seconds, how long would a bill need to be for a person to have a good example of catching it? So I think what this question is asking is, you got a dollar bill, hello, and then maybe you ball it up so that it's, or you roll it up so that it's got less air resistance, but then you take your hand, there's my hand, and if I drop it, through my fingers, there isn't enough time to catch it. And the idea being, well, I don't know, let's see if that's true. How long is the dollar bill? Oops. How long is the dollar bill? Well, anyway, so the idea is there's an object, and it has length L, and it's falling with some acceleration. Acceleration downwards, 9.81. Okay, so when we write down the position as a function of time, we're usually doing it with respect to some part of the object. So let's track the object's bottom lower corner there as it falls through between our fingers. In other words, the question is, how far does this little point on it get in 0.25 seconds? So let's assign a coordinate system. I'll call this x is equal to 0, and I'll have downward or upward increasing, just so that we're increasing. Okay, so let's line this up with our hand and say our initial position is 0, where my hand is. Our initial velocity is 0, I guess. The acceleration is going to be minus 9.81, and so the position as a function of time is 0 plus 0 times time minus 9.81 over 2 times time squared. So 9.81 divided by 2 minus 4.905 t squared. So at time 0.25 seconds, x is going to equal to, and I just plug this into the formula. Okay, so what this tells us is after our reaction time, so they drop it at time t is equal to 0, and then we have to close our fingers. And we assume our fingers are fairly close to each other. This is all about reaction time. How far down does this star piece go, this little end of the note? We see that the end of the note gets all the way down here at, say, 0.3 meters. Which sounds like a small number, but it's 30 centimeters. That's the length of a ruler. So the bill would need to be 30 centimeters long to catch it. Let's see if that's true. I'm just doing an experiment. I got a piece of paper here. Okay. Drop it and try to catch it. Oh wait, it bounced off the table. I guess I gotta start higher. Holy crap. No. Huh. Yeah, people's reaction speed is bad. Try it yourself with a bill at home. It's fun. Next question is question 43, same page. 43 goes like this. A football kicks straight up in the air. It hits the ground 5.2 seconds later. I think implicitly the football starting on the ground. So here's the ground. And then you're kicking it up in the air. So here's your friend who's giving it a kick. And it's going up in the air. And so it goes up. It comes down 4.2 seconds. Wait, what does it say? Question 43. 5.2 seconds later. And the question is, what was the greatest height reached by the ball? Assume it's kicked from ground level. Hold on. Before we go any further, let's assign some coordinates. I'll call its original height x equals 0. And I'll make this increasing, up increasing. All right. So what do I know and what don't I know? I know the initial position 0. I don't know the initial velocity. I don't know the initial velocity. That's 9.81 t. Okay. So the questions are, what was the greatest height reached by the ball? Assume it's kicked from ground level. And what speed did it leave the kicker's foot? So what's the initial velocity? I guess v0. Now, this is actually a pretty fun question. It's fun for a variety of reasons. There's a brute force way of doing it. And then there's an elegant way to do it. My old high school math teacher used to say that it wasn't math unless it had style and grace, but brute force often works. The deal here is that there are two unknowns, literally. Well, to tell you the truth, if we think about these equations as a system of algebraic equations, there's actually four unknowns. X, V, T, and V naught. Two equations, if you had two equations and two unknowns, you could usually solve for it. But in this case, we don't have many. So the brute force method for doing this is to use this equation and the clues. Essentially, what we're saying is we know at what time the object is at a certain position. And so we can brute force our way that through. So at time t is equal to 0.5, it's at position 0. 5.2 minus 9.81 over 2, 5.2. And we can solve this algebraically for v0. Let me do that with my calculator. 5.2 all squared. 5.2 times 5.2 times 9.81 divided by 2 minus sign. Answer. To the left. So that's 25.5 meters per second. This doesn't quite answer our question. The question was, at what time is it its maximum height? Or where is its maximum height? So to answer the question, where is its maximum height, we have to plug this back into the system. So now our position versus time is 25.5 times t minus 9.81 over 2t squared. V is 25.5 times t minus, oh, no wait, hold on. Let's just erase that. Minus 9.81 times t. We know at the top of the arc, v is equal to 0, and that's what tells us t. So we use this equation here to calculate it. 25.5 divided by 9.81, that's 2.6 seconds, and then I can find the position at 2.6 seconds. 25.5 times 2.6 minus 9.81 times 2.6 times 2.6 divided by 2. 33.1 meters. So here is my answer to question A, and here is my answer to question B. That's fun, right? Sure, it's fun. Okay, but it's not the elegant way to do this question. Like I said, this is brute force. It works computationally, it's true, but it's not the easiest way to do it. The easiest way to do it is to use what we know about projectile motion. Specifically, that the motion versus time, the velocity versus time graph is going to be a parabola. And parabolas have axes of symmetries, so you know it reaches this point here at 5.2 seconds, and so it reaches the halfway mark at 2.6 seconds. So it's at its max height at 2.6 seconds. Of course, you knew that already, but just for brute reasoning, you know that it's at max height at 2.6 seconds. And you also know that at 2.6 seconds, v is equal to 0. Because, like I said, symmetry. You know how long it took to reach the same point, so you know where the halfway point is. And you know at the halfway point, it's at its maximum height, so v is equal to 0 there. What that does is it lets you use this equation to figure out the initial velocity, right? Because at this time, the velocity is 0. Whoa. Also, there shouldn't be a t here. What am I doing? Okay. So, weird. All right. So 0 is equal to v0 minus 9.81 times 2.6. And that means v0, it has to be equal to 25.5 meters per second. And then we plug this into the equation. 25.5 times 2.6 minus 9.81 divided by 2 times 2.6 all squared. 25.5 times 2.6 minus 9.81 times 2.6 times 2.6 by 2. 33.1 meters. You know how much less work this took to do? Yeah. Long story short, I mentioned it in class. If you can take advantage of what you know about parabolas and what you know about the symmetries of this motion, you can cut to the chase a lot faster in these types of questions. Has anybody asked anything in the chat? No. Is anybody watching? One person is watching. Hello. Okay. Now, question 61. Question 61 goes like this. Divers compete by diving onto a 3-meter deep pool from platform 10 meters above the water. Let's draw it. Here's your platform. Here's your pool. So I guess I better draw it in blue. So here's the water. All right, so here's our diver up here. That distance there is 10 meters. And then, what's the maximum and the minimum acceleration? Okay, so then it says that there's a 3 meter deep pool. So this distance here is 3 meters. I guess the pool has a flat bottom. All right. So the idea here is the diver's going to dive and hit the water. So you start moving slowly, then you speed up, you go faster, and then as soon as you hit the water, you don't want to keep speeding up. You want to slow down before you hit the bottom. So then they're going to slow down before they hit the bottom. Okay? We know the acceleration going down, 9.81 meters per second squared. We want to know what the acceleration is during this part. Okay? So, how do we figure that out? This type of problem, you can call this a two-part motion problem. It's got two parts, essentially. One type of motion for the first stretch, and then another type of motion for the second stretch. And the deal is that you use the results of the motion in the first stretch to start the second one. So, let's figure out how fast they're moving at the bottom. And to do that, we need a coordinate system. So let's start with our coordinate system. How about if we put, oh, I'm feeling fun. Let's put the origin here at the bottom of the pool. Okay. So for the first stretch, your initial position is, oh, and increasing, decreasing. I'll make that increasing. So your initial height is 13 meters. Your initial velocity is 0. Well, I mean, sometimes they jump upwards, but let's just assume that they fall off, the way I would. And that means the acceleration is minus 9.81 meters per second squared. This minus sign is because this acceleration arrow is in the opposite direction from our increasing arrow. Okay? So the position as a function of time is going to be 13 minus 9.81 over 2t squared. And your velocity as a function of time is going to be minus 9.81 over 2. So the question here is, how fast? What's the velocity as the diver hits the pool? So to answer that question, hold on a second, please. Little mistake there. Okay, so to answer that question, I need to figure out what time they reach the bottom of the pool. This isn't the only way to do it. To tell you the truth, I'm going to do this two ways. So t is equal to question mark when x is equal to plus 3. That's the question. So 3 is equal to 13 minus 9.81 over 2t squared. You can rearrange this equation to get 10 times 2 over 9.81. I moved this 13 over to that side, minus 13, and then I divided it by this coefficient, t squared. So t is equal to 2 seconds. Yeah, we'll stick with 2 sig figs. Oh, fine. I'll do it to more. 2.04. Are you happy now, Mom? All right, so its velocity at that time is equal to 9.81 times 2.04 minus 20 meters per second. So that's its velocity when they enter the pool. So then their velocity is in this direction, their acceleration is in this direction, so that's going to slow them down. And the question is, what's that acceleration? I mentioned before that this is a two-part problem. The easiest way to do two-part problems like this is to keep the coordinate system the same. So your origin is in the same place, your axis is in the same place, but we're going to start a new time. T prime is equal to 0 when hits pool. Okay? So your initial position in this case is +3. Your initial velocity is -20. And your acceleration is unknown. So the position as a function of time is going to be x is equal to 3 minus 20 times t plus a over 2t prime. V is equal to minus 20 plus a t prime. Okay. And then we're going to solve these equations essentially in a similar way as we just did. We're going to say at t prime bottom, v is equal to 0, and at that time, x is equal to 0. They reach the bottom of the pool. And so the question is, what's the value of a? Well, we also don't know what this value is. So, x is equal to 0 is 3 minus 20t prime plus a over 2t prime. I guess I called it b. It's bottom squared. And then 0 is equal to minus 20 plus a b. Okay. So now we're going to solve these algebraically. Let's solve this one for t prime. We'll use the substitution method. So t prime b is equal to 20 over a. And then we'll use the substitution method. 0 is equal to 3 minus 20 times 20 over a plus a over 2, 20 over a all squared. So this becomes 3 minus 40 over a. And this is going to be, 400. And this one's going to be plus 200. 400 squared divided by 2 divided by a. And if we rearrange this, it gives us 3 is equal to minus 200 over a. So a is equal to 200 over 3. Six point 6 meters per second squared. Let's see if that works. Just a second. 20 divided by 66.6. So that's 3 minus 20 times answer plus 20 times 20 divided by answer times 2. Is there a mistake in here? Let me see. Oh, here, hold on. Somebody just asked a question. Hi, Ben. Sorry for disturbing. Can you post the answer key to the practice exam? This is from my 111 class. Hey, 111 student. No. Well, not yet. Maybe I'll do part of the final exam for the 111 thing. The 111 class starts at 3:30. I'll be doing the streaming for that. So come back then. Right now it's Phys112's time to watch me do math. Okay. Okay, so let's see. What's up with this? 3 So 200 divided by 3, that's 66.6. Does that make any sense? Let's see. T prime B would have to be 20 divided by 66.6. That's 0.3 seconds. And then if I plug these together, it's 20 plus 66.6. Okay, so the velocity checks out. What about the position versus time? 3 minus 20 times 0.3 plus 66.6 times 0.3 times 0.3 divided by 2. Oh, it works. Okay, so these answers work. Check mark. Okay, so I said that there was an easy way and a hard way to do this. That's the easy way. Sorry, that's the tricky way. But you'll note something here, which is that over and over and over, I have essentially a relationship between the distance and the speed. Let me explain it this way. I'll do it down here. Your constant acceleration your position as a function of time is going to be a parabola, right? And that means that it's symmetric. So at any position, there's going to be two velocities, one and then the other, and they're going to have an equal speed, right? And so, long story short, because the speeds at any position are going to match, different velocities, one's going one way, the other's going the other way, but the same speeds, there's a relationship between speed and position. How do you figure out what the relationship between speed and position is? You essentially crunch these, you take the equations, x is equal to x naught plus v naught t plus a over 2t squared, and v is equal to v naught plus at, and you solve them for t. Or you solve one for t. You solve this one for t, and then you replace. Watch what happens. This becomes v minus v naught all divided by a is equal to t. I'm going to plug that back into this equation. X is equal to x naught plus v naught times v minus v naught over a plus a over 2 v minus v naught over a all squared. I'm going to move this x to this other side just for fun. X minus x naught, just to get it out of the way. I expand each of these using FOIL, just multiply through. V naught times v minus v naught squared. Oh, geez. All divided by a. Plus, and then you FOIL this one out. So this becomes 1 over 2a v squared minus 2 v naught v plus v naught squared. And then you want to combine them. And I'm going to combine them by making the denominators match. So I'll multiply this one top and bottom by 2. Okay. So now the 2a matches the 2a, and I can write them all as one fraction. So that becomes v squared minus 2v naught v plus v naught squared plus 2v naught v minus 2v naught squared. And we get some cancellation. This cancels with this. And these two will partially cancel out. And so we get v squared minus v naught squared over 2a x minus x naught. And then you rearrange that and you get 2a x minus x naught v squared minus v naught squared. So this is an equation that you can use. Sometimes it gets rewritten in terms of initial and final velocities and positions, but this is the relationship between position and speed. Okay. So sometimes, so this works with any constant acceleration, and so sometimes this equation gets rewritten like this: v final squared minus v initial squared. Now, keep in mind, this looks like a whole new equation, but it's not. It's just literally these two algebraically replaced. That said, we can still use them. So we wanted to know how fast it was moving at this point. So we go the acceleration. It's like 2 times the accelerate 2a x final minus x initial is equal to v final squared minus v initial squared. All right, let's use it. 2 minus 9.81. The final position was 3. The initial position was 10. So you add those up together and you get nope. Sorry. I just made a mistake there. It's not 10. It's supposed to be 13. All right. 2 times 9.81 times 10. So this is 19.6. And then that's v final squared minus v initial squared. V initial in this case is 0. So v final is equal to the square root of that. Square root answer 14 meters per second. Whoa, what? Did I make a mistake? Maybe I made a mistake. Ten times 2 divided by 9.81 square root answer. Oh, I forgot to take the square root here. That's why these numbers are all weird. This number is supposed to be 1.42 seconds. So that's the velocity. That makes a little bit more sense. I guess it's minus. Hold on. Let me read this. So the thing about that equation is it doesn't tell you the velocity. It tells you the speed. So you have to put in the sign by hand. That said, you know his initial velocity here now, and you know his final velocity. So v initial is equal to minus 14. V final is equal to 0. X initial is 3. X final is equal to 0. And so you can plug these numbers into this system. So it's 2a. X final minus x initial is minus 3. V final is 0 minus 14, 1, 4, all squared. So 14 times 14 is equal to that, divided by 2, divided by 3. $32, which makes a lot more sense than 66. I'll tell you why it makes more sense. Just looking at this, you're accelerating down over this distance, and then in this distance you have less than a third of the distance to decelerate. So to get to the final velocity here, you do it over 10 meters. And to go from that initial speed to 0, you only have 3 meters. And so, just eyeballing it, the acceleration should be something like 3 times gravity, which is why when I calculated this bot, you ended up, and I saw that crazy number, I was like, that acceleration's way too high. This is about 3 times gravity, so that makes sense. All right, next question, I guess. Which question was this? 63? Oh, that was 61. Way too much time talking. All right. 63. Okay. 63 goes like this. A rock is tossed straight up with speed 20 meters per second. When it returns, it falls in a hole 10 meters deep. So here you are, next to your 10-meter hole, and you throw a rock in the air. Okay. Oh, initial velocity is 20 meters per second. Okay, so first trick to all these is to always choose a reference frame. So let's choose a reference frame so that x is equal to 0 down at the bottom of the hole. And you know what? I'm feeling kind of pressed for time, so I'm going to rely on this equation to answer some of the questions. So your initial position, 0, is plus 10. Oh, yeah, increasing. Okay, 10 meters. And your initial velocity is plus 20 meters per second. And your initial acceleration is minus 9.81 meters per second squared. Okay. So, what's the rock's velocity as it hits the bottom of the hole? I'm going to use these equations. So when it hits the bottom of the hole, its velocity is going to be negative velocity. So I have to keep in mind, because this equation only tells me, like I said, it only tells me the speed. I need to then interpret the number I calculate. So 2 times minus 9.81, your final position is 0, your initial position is 10, your final velocity is unknown, your initial velocity is 20 squared. 9.81 times 2 times 10, so that's 196.2 VF squared minus 400. Bring the 400 to the other side, take the square root. 24 meters per second, but like I said, that's the speed. The velocity, I then have to put that in by hand, minus 24 meters per second. How long is the rock in the air from the instant it's released to the bottom of the hole? Okay. There's 2 ways to answer this question. There's the tricky one and the easy one. So the brute force is you say, this particular question is a position time question. At what time is it in a certain position? So the equations of motion are okay. And we want to know, find t bottom when x is equal to 0, which is the location of the bottom of the well. And so you take this equation and you solve it for t. You can use the quadratic formula if you want. Pretty cool. Okay, the elegant way to solve this question is to say, I know the velocity at bottom of the well. And so instead of saying, oh, this is a position versus time question, because I have this particular piece of information, I can use the velocity versus time question to solve it. Minus 24 is equal to 20 minus 9.81 times t. Both will give you the same answer. Actually, this one is going to, doing it this way is going to give you two answers, a positive time and a negative time, and you have to choose the positive one. But this other way only gives you one value of time. Minus 24 minus 20 divided by 9.81. So time is 4.49 seconds. Done. Next question. Anybody have any questions in the live chat? Okay, hold on. Let me refresh my QuickTime player. It's gonna automatically shut off if I'm not careful. Hold on. There. Okay. Let's keep going. Now on to page 103. Question 11. What do you think of online office hours? I think it's pretty fun to just sit down for an hour or so a week and just do physics questions. I kind of got into physics because first year physics is so much fun. You're like, physics, first year physics isn't fun? Yes, it is. You just don't know. You just don't know how much fun it is. There's always an answer. Use it using cleverness. Okay, 103. Question 11 goes like this. Draw each of the following vectors, then find its x and y components. All right, so question 1 is 100 meters, 45 degrees below x-axis. So it's like that. It's 100 meters long, and that angle is 45. I'll draw them all. Drawing is fun. B is 300 meters per second, 20 degrees above the x-axis. So there's your V. That's 20 degrees. And C is acceleration 5 meters per second squared in the minus y direction. So I guess I'll draw it in red. Acceleration like that. I forgot to write that this is one's 300. Okay, so how do you do it? The answer is we just break it down like a triangle. So a triangle I would draw would be made out of sides like this, right angle triangle, right angle triangle, right angle triangle. But when I break down a vector, it's a little bit more than that. What I want to do when I draw these triangles isn't just draw sides. I want to draw little arrows. Just imagine that you're starting from this place, and you're walking from here to the right and then up. And the arrows display the direction you're walking. Okay? We're going to make reference to them soon. The length is the same. So for instance, to calculate this top one, I'm going to use 100 times cosine of 45. 100 times cosine of 45. That gives me 70.7 meters. Similarly, this one is 100 times sine 45. Get out calculon. Calculon says 70.7. But this isn't the final answer. These just tell me the lengths of the sides, the magnitudes of the sides. But the reason we draw the sides as vectors is because, as arrows, is because they're vectors. Just walk pure east, walk pure south. You dig? So for that reason, hold on. I called it the D vector. So for that reason, D vector in the x direction, D vector in the y direction, we need to assign a sign to it. So this number is the magnitude, and it's moving to the right, so it's positive. This one is moving down, so it's negative. So similarly, use trigonometry to find these two sides. Let me do those now. 300 times sine of 20. That's 102.6 meters per second. The sides have the same units as the top does, as the hypotenuse rather. 300 times cosine of 20. So this bottom one is 281.9 meter per second. And then we have to assign a sign to each of these. Vx, Vy. So the one in the x direction, that's moving in the positive direction, that arrow is, so it's plus 281.9. And this one's moving in the positive direction, so it's plus 1. Oh, that's not a number. 102.6 meters per second. This last one is a gimme. And by that I mean it's easy peasy. Its x component is 0. Its y component is 5. But it's in the negative y direction, so minus. Done. All done. That question's done. Not too hard, is it? No, sir. Next question. Question 13. Each of the following vectors is given in terms of its x and y components. Draw the vector, label an angle that specifies the vector's direction, then find the vector's magnitude and direction. I think when they say label an angle, they mean draw an angle on the picture, okay? So let's try this. Okay, so draw your x and y axis. X, y, and this looks tricky, but it's not quite. You go 20 in this direction, and then you go plus 40 in that direction, 40. So the vector is there, and that's the angle I'm going to be using. Okay, so the length of the vector is just the hypotenuse of this triangle. So square root 20 squared plus 40 squared. Hey, hey, 20 times 20 plus 40 times 40, square root. And the angle, I'm going to use arctan. (63.4 degrees). Any questions? That's pretty straightforward. Let's see how the stream's doing. Stream's doing good. Man, the stream is strong tonight. I'm pretty happy with this stream. Usually it's kind of finicky, but tonight it's good. All right. 2.0 meters per second squared. AY is minus 6.0 meters per second squared. So how do we draw this? Just draw your x and y. Right, I forgot. I have this thing. Hold on. Let me try it. That paper. Oh, yes. Well, maybe closer together. Now we're talking. So start wherever you want. Let's start here. Okay. I'll do it in red. So first you go this one, and then you go this one. So 2 is this far. And minus 6 is 1, 2, 3, 4, 5, 6. Okay? So my vector is like that, and that's the angle I'm going to find. Okay? So that's 2, and that's minus 6. And so the magnitude, which is just the hypotenuse, squared plus minus 6 squared. 2 times 2 plus 6 times 6, square root of 40. And the angle, I'm just going to use arctan to do it, 6 over 2. 71.5 degrees. Yeah, that looks 71.15 degrees. All right, any questions? Good, let's move to the next question. If you have any questions, write them down in the live chat, and then I can stop, and I can explain what I'm doing better. But if you don't, I won't. 26. Oh, great, it's a projectile motion question. We didn't cover enough projectile motions in class. We did a little bit. You have the basics of it. And at its heart, it's just algebra. Well, no, at its heart, there's a bunch of conceptual understanding things. But a lot of the lessons that we learned from talking about free fall, which is one-dimensional projectile motion, show up in these projectile motion questions. So let's do this one. I quote, an object is launched with an initial velocity 50 meters per second at a launch angle of 36.9 degrees above the horizontal. Oh, son of a bun. Is this really question 26? Why did I choose this one? Oh, God. I don't want to. Yeah, this question's bad. I guess I signed up to do it. All right, fine, whatever. So, there's your velocity, 50 meters per second, and this angle here is 36.9 degrees. Okay, so where should we put the origin? It didn't specify because this question's bad, so I'm going to put the origin here. Okay, that means x0 is 0 and y0 is 0, and I'm going to put that is increasing and that is increasing. Okay, so the acceleration vector in the x direction is going to be 0, and the acceleration in the y direction is going to be minus 9.81 meters per second squared. So the only thing to do is to break down this guy into its components. $50 times cosine 36.9 is equal to 40 meters per second. And 50 times sine of 36.9 is equal to 30. Cool. Okay. So we can break all this information down as equations of motion. So the velocity in the x direction, velocity in the y direction, position in the x direction, position in the y direction. I'll just call it y. All right. I'm going to try something. Oh, hey, Ben, which list of exercises are you using? The exercises are listed right below the video. It says Phys112 October 3, and then it says questions page 69, question 39, 43, 61. So the questions are always listed right below the stream. So right now we're on question 26, which is on page 103 of your textbook. Okay? All right, let's see if this stupid thing works. V0 x plus a x times time. V0 y plus a y times time. X0 plus V0 x times time plus a over 2 times squared. Y0 plus V0 y t plus a, I guess that's ax, ay over 2t squared. Okay, so I don't know why I'm doing this. We'll try a fill in the blank thing, because that's kind of how I think about this. A lot of the physics is about understanding what's going on and translating your understanding into a set of equations. But the sets of equations that we're using aren't particularly original. Physics isn't about memorizing which equation to use when, but if you know which equation... Oh, somebody called Cup CS just wrote, midterm tomorrow, 6 people watching. Midterm tomorrow, 6 people passing. That's not quite true. This is the Phys112 stream. The Phys111 stream is going to start in about 20 minutes. So none of the people watching right now should have a thing tomorrow. Although if you want to, you can. A lot of this is crossover. But yeah, this is Phys112. So we'll start our own stream for 111 soon enough. But please don't make assumptions about the number of people passing. Who knows how many people are panic watching this though right now, saying, what questions in the textbook are you doing? I don't know. Okay, so let's do these questions. V0x, so that's 40, and the acceleration is 0. So plus 0 times time. V0y is 30, and the acceleration is minus 9.81 times time. The initial position is 0. Initial position is 0. Initial velocity is 40, 30 times time. Acceleration is 0. T squared. And the acceleration is minus 9.81 over 2t squared. So, what you're going to do this question is make a table of values of the velocity and position as a function of time. X, t is equal to 0, 1, 2, 3, 4, 5, y, vx, Vy. So these are all going to be 40, 40, 40, 40, 40, 40. So this one's 30. 30 minus 9.81 is equal to 20.2 minus 9.81 is equal to 10.4, I guess. Minus 9.81, 0.6, minus 9.81, minus 9.24, minus 9.81, minus 19.01. And the x position is going to be 0, and then 40, and then 80, and then 120, and then 160, and then 200. And the y position is going to be, so you got to get your calculator out. Can't quite do this in your head. 30 minus 9.81 divided by 2. So this is 25.09. And then point 2 is 30 times 2 minus 9.81 times 4 divided by 2. So then it's 40.4. And then 30 times 3 minus 9.81 times 9 divided by 2, 45.6. And then times 4, 30 times 4 minus 9.81 times 4 times 4 divided by 2, 41.5. And then 30 times 5 minus 9.81 times 25 divided by 2, 27.4. And then you graph these. This will put my origin here. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Alright, so let's draw the positions at each of these times. Start there at t is equal to 0. And then t is equal to 1, you're at 40. 1, 2, 3, 4. And 25. 1, 2.5. So you're there. Time 2. 1, 2, 3, 4. And you're at 40. 1, 2, 3, 4. Time 3. You are at 120. 20. And at 45. 45. And 4 later, 1, 2, 3, 4. You're at 41, which is there. And 200, you're at 27. 1, 2, so there. And then so you can draw 1, 2, 3, 4, 5. We can also sketch their velocities on the scale because their velocities are in. Alright, so the velocity at this time is going to be 40. 1, 2, 3, 4 times 30. 1, 2, 3. So the velocity is like that. This next time, the velocity is 40, 20. 1, 2, 3, 4, 20. 1, 2. Next one, the velocity is 40.06. So it's 1, 2, 3, 4. 0.06 is like there. No, sorry. I did that wrong. 40 and 10. So 1, 2, 3, 4, and 10 is there. And the next one is 40.06, which is pretty much horizontal on this poorly drawn graph. Next one's 40 minus 9.81, so it's 40, something like that. And then the next one is 40 minus 19. 1, 2, 3, 4. Just like that. So one thing to notice here is the velocities that we drew. Those are the instantaneous velocities, so they don't go to the next point. In fact, in this case, they're always going to overshoot the next point, and that makes sense because the instantaneous velocity is continuously changing. Okay, so next question. 27. A ball thrown horizontally from a 20-meter high building. So here's your building, 20 meters. So here you are, being a jerk, throwing a rock off a building. Yeah, I know it says a ball, but whatever. You throw it horizontally, so its initial velocity is going to be like that. V0 in the x direction is 5. Oh, this is fun. Fun. Make a sketch of the ball's trajectory. Okay, so it's going to go down. Maybe that isn't even very good. It's got to be more parabola shaped. Okay. Okay. Draw a graph Vx of the horizontal velocity as a function of time. Well, the horizontal velocity is going to be, let's see, it's at 5 meters per second, and it's not going to change. Vx meters per second time. Draw a graph Vy, the vertical velocity as a function of time. Include units on both axes. T in seconds. meters per second Vy. So Vy starts at 0, and then I guess it's going to get more and more negative. Wait, hold on. It's constant acceleration. Acceleration is the slope of this velocity. So it's going to be a straight line. Okay. How far from the base of the building does the ball hit the ground? What they're asking for is like this distance here. X. X as a function of time is going to be, oh, hold on. Let's get some coordinates in here. How about if the origin is down here? Your initial position is 0. Y's initial position is plus 20. I guess increasing that way, increasing that way. Just for sanity's sake. Your velocity in the x direction is 5 times t. Your velocity in the y direction is 0. Minus 9.81 over 2t squared minus 0 t squared over 2. Got it? So we want to know at what time it hits. It hits when y is equal to 0. So I can use this equation to figure out at what time it hits. Don't do a hit. 20 times 2 divided by 9.81. That's 4.1 seconds later. Oh, I forgot to take the square root again. 2.01 seconds. Okay. And then I can plug this into this equation here. X hit is equal to 5 times that answer. 10 meters. It hits 10 meters from the bottom of the thing. Questions? And next question is 21. Okay, so these are the relative velocity ones. I love relative velocity. The thing about relative velocity is if you use equations too much, if you overuse the equations, it's really easy to get them switched up about whether you're adding or subtracting. So it's actually pretty helpful to just draw a diagram and consult the diagram when you do it, and let the diagram tell you whether it's adding or subtracting. Anita is running to the right at 5 meters per second. Balls 1 and 2 are thrown towards her at 10 meters per second by friends. So that's 1. And that's friend. 2, 10 meters per second. Standing on the ground. According to Anita, what's the speed of each ball? Okay. So there's a couple ways to do this. You can do it algebraically, or you can't. So let's do it one at a time. Ball 1. The velocity of ball 1 relative to the ground is equal to 10 meters per second. The velocity of Anita relative to the ground is 5 meters per second. I'm looking for the velocity of the ball 1 relative to Anita. All right. So algebraically, this goes V1G plus VGA. Except that we don't know VGA, and the opposite is 1G minus VAG. And so this is 10 minus 5. 5 meters per second. Ball 2 is going to be 15. Okay, so one question you could ask is, where are these coming from? Well, this is just kind of the formula. The rule, as John Hopkinson puts it, is you're adding velocities. If this letter matches, you can combine them. Another way to see this is to just compare them. How should I put it? We know what we want to find the velocity of the ball relative to ball 1. We want to find the velocity of ball 1 relative to Gina. Nope. Relative to Anita. And what we have is the velocity of ball of Anita relative to the ground and the velocity of the ball relative to the ground. And we could say, how do I combine these three into an equation, into one equation that essentially follows this rule? And then what you say is you go like, oh, well, these two have matching first and lasts, so V1A plus VAG is equal to V1G. That's how the rule goes. And we know some of these. I want to know V1A, but I know that this is 5 and this is 10, and you can rearrange this and get 5. So that's one way to do it. Another way is to say, okay, the ball is going like that at 10 meters per second. Anita is going like this at 5 meters per second. How much faster in this direction is the ball going than Anita? The ball's going 5 meters per second faster. And so the ball is going to catch up at 5 meters per second. That's one way to do it. Let's try that for the second one. Anita. Whoa, what's wrong with my pen? Oh, it's okay. Anita goes like that at 5 meters per second. The ball number 2 goes like this at 10 meters per second. How fast is the distance between them changing? Well, the distance between them is decreasing at 15 meters per second. How do you calculate that? Well, I want to know ball 2 relative to Anita. The thing I know is the velocity of Anita relative to the ground and the velocity of ball 2 relative to the ground. How do I combine these three in order to follow this rule where these letters match and I can add them? These two letters match. This letter here and this letter here match, but they're in the wrong place. I need one in the front position, one in the back position. So this means 2A plus VA is equal to V2G. And I know some of these. I know that this is plus 5. And I know that this is minus 15. Nope, I looked in the wrong place. I don't know where that came from. Minus 10 meters per second. And then I just combine them. Minus 10, minus 5, minus 15 meters per second. So, long story short, Anita's running away from this ball, so she doesn't think it's moving very fast, and she's running towards this ball, so she thinks it's going faster. Okay, question 23. A boat takes 3 hours to travel 30 kilometers down a river and then 5 hours to return. How fast is the river flowing? We are presuming that nobody is doing any drinking over the course of the river journey. Okay, so you got a boat, and the boat's going in the stream. And whether it goes this way or it goes this way, it's always traveling with some speed relative to the river. V boat relative to the river. So going. Yeah. So journey 1 goes that way. Journey 2 goes that way. So let's say that this is a minus unknown v. VBR vector. On the way home, it's increasing. On top of that, the river's flowing. Which direction is the river flowing? My guess is the river's flowing downriver. V river ground. I'm guessing that the river's flowing down because it takes less time for the boat to go this way than it does to go that way. Okay? So V river relative to the ground is equal to does it say? No, it doesn't. I'll call it W. And it's going in the minus direction. V river ground is minus W. Okay? So the boat's traveling in the river, and the river's traveling in the ground. So the boat's velocity relative to the ground is V boat river plus V river ground. So it's going to be plus minus V minus W, and boat ground is going to be V boat river plus V river ground. So it's going to be plus V minus W. Okay, so what clues did they give us? They gave us how far the distance was. 30 kilometers. So I'll start x is equal to 0 here. But delta x is equal to plus, no, minus 30. Because down's negative. Careful, careful. Minus 30. And you did it in delta t is equal to three hours. Delta x here is equal to plus 30, because you go 30 straight upstream, and delta t is equal to 5 hours. So V boat relative to the ground is equal to minus 30 over 3. That's minus 10 kilometers per hour. And the boat ground on the second half is plus 30 divided by 5. That's plus 6 kilometers per hour. And so the question we're trying to figure out is, what's this value V? Whoa, no, hold on. Back. What's this value V algebraically? So V minus W is equal to minus 10. Let me convert that more conveniently to V plus W is equal to plus 10. And v minus w is equal to plus 6. So, and I've got two equations and two unknowns. So I need to solve them. I'll solve them by adding these together. 2v is equal to 16. V is equal to 8 kilometers an hour. And W then needs to be 2 kilometers per hour. Hooray! All right, that's it for this week's clicker thing. For those of you watching the stream because you want to see Physics 111, I'll pause this stream and then I'll start a new stream with a different title and also list the questions. All right? Stop streaming.